Good evening, everyone. We'll wait for 2 more minutes before starting the session. Hello, everyone. So, this is a live session for the NPTEL course Computational Fluid Dynamics conducted by Professor Sreenivas Jayanti from IIT Madras. So, in this session, we'll solve few problems relating to the course. At the end, if you have any doubts related to the problems, you can ask. And this is Ankara Kartika from IIT Hyderabad. I am a PhD scholar. So we'll move on to the problems to be discussed in this session. If you have any doubts, please note it down. We'll discuss it at the end. So yeah, like so this is the live session one. We'll discuss few problems relating to the assignments and everything. Once again, someone else wants to join, we'll just add them. This is question one. In this question, it is mentioned that which of the following formulae is a good approximation for dou square u by dou y square at grid point I comma j. So we all know how to approximate the partial differential equations. We'll see which of the following options are applicable for this context. So normally in a discretized form, to get the value at I comma j, we use all the neighboring points. So this is a second order differential derivative. So we use central difference scheme. So if we need to get the value at I comma j, that is dou square u by dou y square at I comma j, when we use the central difference scheme, we use it like the point at I comma j minus 1 and the point value at I comma j plus 1 needs to and plus together with the I comma j. All these together gives the second order difference for dou square u by dou y square at I comma j, and since it is with dou y square, we get delta y square. The thing to be noted is it is del y square. So the change happens with j factor, that is it varies with along the y axis. So on comparing these four options, that is first option, it is given that uj minus 1 I uj comma I uj plus 1 I by del y square. Here it varies in the I or x direction, so this is not applicable. And in the next case, it is given ui j minus 1 minus 2 ui comma j plus ui j plus 1. Although the first factor is right, it is given by delta x square. Since this is changing with respect to y and it is changing given as x square, this is also wrong. And in the option C, it is given that ui comma j minus 2 ui j plus 1 plus ui j plus 2. So this one is slightly applicable if the point is ui comma j plus 1. But since we are obtaining the value with respect to point ij, the option C is also wrong. Option C is right if in case we are getting differential values at I comma j plus 1. All three options are wrong. So the correct answer is none of the above. Answer option D is the correct answer. So next question is, consider a steady developing laminar flow in a circular pipe. Which of the following statements is true for this flow? Option 1, first statement is it is given that velocity profile changes axially. And in the second option, it is given velocity profile changes radially. In option 3, it is given pressure varies linearly in the axial direction. And in option 4, pressure remains constant. So which of the following statements are true in this case? Like for a steady developing laminar flow in a circular pipe. So we'll see which of these statements how it is applicable in this case. So this is the profile for the velocity distribution in a circular pipe. From this, we can observe that for a steady developing laminar flow, the velocity profile, it keeps changing axial direction till it attains the fully developed flow. Here it is after fully developed flow, it is after fully developed flow, it does not vary axially. It does not vary axially. But in the before that, it changes axially also. And the velocity profile, it also changes radially. Like we can see that near the wall, it is almost with the from the no slip condition, it is in 0, and towards the center, the values are high. Velocity profile also changes axially as well as radially. This is the pressure distribution. One second. This is a pressure distribution curve for the flow in a circular pipe. So from this, it can be seen that like a pressure, it does not remain constant over the flow region. It keeps on changing. And also in before fully developed flow, the pressure, after fully developed flow, the pressure it varies linearly in the axial direction, whereas before that it does not vary linearly. There is some abrupt decrease in this region, after which only it attains the linear change in the axial direction. So these were the 4 options that were given in this question. So from the profile, we can see that velocity profile changes axially. This one is true. Velocity profile changes radially. This one is also true. Whereas pressure varies linearly in the axial direction. This is false. Pressure does before fully developed flow, it does not vary linearly. Whereas pressure is also not constant in this flow system. So the answer is option A, which is statements 1 and 2 are right. So next question, we'll move on to question 3. In question 3, we have that consider a one-dimensional flow governed by d square u by dy square is equal to c. Over a height h, the interval h is divided into 30 equal segments. The upper wall moves to the right at a speed of 1 meter per second, while the lower wall is stationary. The number of discretized equations are. So this question tells us about how many discretized equations will be there in a system if it is equally divided into 30 segments. So for this, we'll see that consider this part of the system alone, where if it is divided into consider this part of the system alone, where it is equally divided into 3 segments. So we have 4 discretized points. We'll start from the first. So in this question it is asked like d square u by dy square is equal to c over a height of h, where h is divided equally into 30 segments, and we got the boundary condition at the top and the bottom wall. So the question asks how many discretized equations will be there for the system. So in order to see that, we'll see a small system where it is equally divided into 3 segments. If there is 3 segments, we have 4 discretized points, and from this points we know if it is the whole system, we know the value at the top and the bottom. So the boundary conditions we will be knowing the velocity values at the top and the bottom. So the remaining 2 points are left out. So the 2 discretized equations are framed in this for a small for this small system of equations. So if this system is extended into a large system of 30 segments containing 30 segments. Since in this if when it is divided into 3 segments, we got 4 equations. I mean 4 points. So similar manner, if it is 30 segments, there will be 31 points, and in that case too we'll be knowing the boundary conditions, that is the velocity at the upper wall and the lower walls are given. Where here it is given that velocity at the upper wall moves at the speed of 1 meter per second while the lower wall is stationary. So then basically then the number of equations will be, we'll be subtracting those two conditions from this, and 31 minus 2, it will be 29. So the answer is option A, which is 29. The correct equation governing flow in a fully developed flow through a rectangular duct is, we have got few options. We will be seeing which one of this is correct. So for a fully developed flow through a rectangular duct, we'll consider the flow in the x direction. Only u velocity will be there, whereas u is a function of y and z, and v and w velocities will be 0. So considering this, we'll apply it to the Navier-Stokes equation, and the equation is given by this rho dou u by dou t and u dou u by dou x plus v dou u by dou y, w dou u by dou z is equal to minus dou p by dou x plus rho g plus mu into this system. In the system, we know that v and w are 0. So this term and this term becomes 0, and it is a steady state. So it does not change with time. So this term also becomes 0, and this is u dou u by dou x. Since u does not vary with x, this term also becomes 0. So on the whole, the left hand side completely becomes 0, and it is equal to minus dou p by dou x plus rho g. Since we are considering flow through a rectangular duct, gravitational flow is not considered. I mean gravitational effect is not considered over here. So this term also becomes 0. And on the this term, the remaining term will be mu dou square u by dou y square plus dou square u by dou z square, since u does not vary with x. So this is the form we get. So on interchanging this, whereas this goes that side and mu also goes this side, we get this form of equation. So this is the equation, that is option B is the correct answer for this question 4. So next we'll get that consider a fully developed laminar flow through a square duct of side L, and that through a rectangular duct with to height ratio of 2 such that both of them have same cross sectional area. If the same fluid flows both the ducts, if the same fluid flows through both the ducts at the same volumetric flow, which of the following statements is true about the two flows? So and the answer given is governing partial differential equation is the same. The wall boundary conditions are the same, though these are applied at different locations. The flow domain is the same. So what they have given is, we are considering a fully developed laminar flow through two different systems. One is a square duct of side L, and another is through a rectangular duct with to height ratio, that is with bottom width to height ratio is 2 in the rectangular duct. both of them have the same cross-sectional area. The cross-sectional area of flow is same in both the systems. If the same fluid flows in both the systems, in the square duct and the rectangular duct, the same fluid is flowing at the same volumetric flow. Which of the following statement is true? The governing partial differential sorry, the governing partial differential equation is the same, which is true. The partial differential equation is the same. We are not Since it is a rectangular coordinate system, the partial differential equation, I mean, it does not, equations remain the same. The application with respect to points will be differing, but the basic governing equation is the same in this case. Next is the wall boundary conditions are the same, though these are applied at different location, which is also same. Like different locations we are applying the boundary conditions, but the conditions like bottom and the top, where velocity values will be given, remains the same. The flow domain is the same. Flow domain is not the same because here it is a square duct of same side, whereas in the rectangular duct the height to the width ratio is 2, such that the flow domain is not the same. So out of all these four options, one is correct, two is also correct, so third one is false. So this is option C, which is correct. Since both of these are correct, option C is the correct, and option D is also wrong because third one is wrong. So we'll then now move on to one case and see how it is, how we are able to solve the questions asked from this case. So we'll first read and understand what is given in the case, followed by few questions on this case. So what it is given is that you wish to solve a problem involving steady state heat conduction in a slab of thickness L. So it is given that you wish to solve a problem involving steady state heat conduction in a slab of thickness L. The wall has volumetric heat generation rate Q. If the height and breadth of the slab are very large compared to L, then one can assume the problem to be one-dimensional. For the case of constant thermal conductivity, the governing equation governing temperature distribution takes the form Q is equal to K dt square, d square T by dy square. K is the thermal conductivity, T is the temperature, Y is the distance in the thickness direction from one end of the wall, and Q is the volumetric heat generation rate. For this case, the calculation domain encompasses the region y is equal to 0 L with both boundaries included in the calculation domain. So we'll first see what this case is about and what are all the information we can generate or we can get from this case on reading it for the first time. So It is mentioned that you wish to solve a problem involving a steady state heat conduction in a slab of thickness L. We'll take the slab to be of thickness L. The wall has a volumetric heat generation rate Q, and it is mentioned that height and breadth of the slab are very large compared to L. That is, its thickness is very small compared to its height and breadth. So we can assume the problem to be one dimensional. For this case of constant thermal conductivity, it is mentioned the equation governing temperature distribution takes this form. So with this condition, we can infer that it is the since the thickness is very low, the problem is one dimensional problem, and Q is a constant thermal conductivity, and so the equation governing temperature distribution is this equation. Here in this equation, Q is the volumetric heat generation rate, K is the thermal conductivity of the material, T is the temperature, and Y is the distance in the thickness direction. That is, this Y comprises from 0 to L, where L is the thickness. So we'll see what are all the questions that can be framed from this case, and we'll solve few of the questions. For equation 1 to be dimensionally consistent, the units of K should be, what is the units of K? So it is given that since we know that Q is equal to K d square T by dy square. So for this equation, to get the dimensionally consistent form of the equation, what should be the unit of Q in this equation? So we'll solve them by this. So the answer is given as B. We'll see how. So this is the equation. Q is equal to K d square T by dy square, where K is the thermal conductivity. Its unit is watt per meter Kelvin. Temperature is in Kelvin, and distance is in meter, and Q is the thermal heat generation. We should find the unit for this. So we'll substitute the known units in this equation for K, T, and Y. That is, K is watt per meter Kelvin and T is Kelvin by meter square. Watt is nothing, watt is joules per second, and joules is Newton meter. So on substituting all this, we'll get the equation of Q to be kg per meter and second cube. So the answer is option B, kg meter per meter second cube. Kg per meter second cube, where we'll substitute, I mean in this equation we to get the dimensionally consistent unit for Q, we need to substitute the other known units in this equation, where we know the units for thermal conductivity, temperature, and distance Y. So we have put all this in this equation and cancel out the units for this, and we'll get the unit as kg per meter second cube. So next question, which of the following cases is not permitted by the equation 1? Equation 1 is K d square T by dy square is equal to Q. In this it is given that first statement is thermal conductivity is dependent on temperature. Thermal conductivity is dependent on location inside the calculation domain. And option C is both. Option D is neither. The thing to be noted is they ask which of the following cases is not permitted. We should see that not permitted by this equation. In this equation, K is the thermal conductivity. So this is the case where it is a one-dimensional problem. So we will see which of the cases is not permitted. Thermal conductivity is dependent on temperature. This is not true in this system. Thermal conductivity is not dependent on temperature. Thermal conductivity is dependent on location inside the calculation domain. No, it is not dependent on location inside the calculation domain. Where it is in the problem statement itself, it is clearly mentioned that for the case of constant thermal conductivity here is constant. So it is not dependent on temperature, not dependent on a location inside the calculation domain. And option C is both, option D is neither. Option C is the correct answer. That is, both of the statement is not permitted by this equation 1. Next is the one more equation for it.
Excuse me, ma'am.
Yeah.
Can you please show me the last question? Okay, ma'am. Thank you.
Yeah. This is question 8. For equation 1 to be used to find the temperature distribution along the length of the rod, which of the following conditions must be met? Equation 1, as we all know, it is Q is equal to K d square T by dy square. Uh, for that equation to be satisfied, what are all the conditions that must be satisfied to for that equation to be applicable? Sorry. It is the rod must have L by D, where which is very greater than 1, where L and D are length and diameter of the rod. And option 2 is rod must have its curved side insulated. The rod must have a rectangular cross section. One thing which was mentioned clearly in the case statement is height and breadth. In this system, it is a rectangular system where the height and breadth of this are very large compared to L, so that the problem was assumed to be one dimensional. So in the similar case, for the question 1, equation 1 to be satisfied for finding temperature distribution along the length of the rod, same case, for finding the temperature distribution along the length of the rod, the following conditions must be, what are the conditions that must be satisfied? So we'll see which is fine. So in this first statement, it is given L by D, which is very greater than 1. Length is very much higher compared to the diameter of the rod. So it is a one-dimensional problem. So this must be satisfied for sure to use equation 1. Next is rod must have its curved side insulated. And option 3, it is rod must have rectangular cross section. So option 2 and option 3 need not be satisfied for using equation 1, whereas option 1 must be satisfied for sure to use the condition of one dimensional problem. So option 1 must be met, that is 1 only. So option A is the right answer. Next is
Ma'am, but in the given question, it is given to us that width and height. So how is their diameter there?
sorry. No, this is
Ma'am,
a different case similar to the rectangular with problem. Here we are moving along the length of the rod. Like to get it along the length of the rod, diameter must be very small.
okay, ma'am, got it.
Yeah. Next is the one. This is not related to the case. This is a separate problem. So here it is mentioned that you wish to solve a set of linear algebraic equations written in the form of Ax is equal to b using the Gauss-Seidel method. Which of the following?
Hi, ma'am. Good evening.
Yeah.
Ma'am, are you presenting the screen? Because I cannot see anything. I have joined just now.
Okay. You can't see.
Yeah, I am not able to see your screen, ma'am.
Okay.
And
What?
also, we have which assignment questions, ma'am? Which
Uh,
assignment number?
these are mostly taken from assignment 0, like practice problems, and some other problems taken for. I mean, these are not related for few problems that would help you in solving assignment 1 and submitting it.
Yeah.
Okay, I'll just stop presenting and present again. You just check if you can see.
Yes, ma'am.
Can you see now?
Yes, ma'am. Yeah, I can
Okay,
see now. Thank
okay.
you, ma'am.
Yeah, sure.
Ma'am, is this
Yeah,
call recorded? Can we see the
yeah,
notes
it is
later also?
yeah,
Because
yeah, yeah,
I
yeah,
missed
it is.
some of them. Where can we find it, ma'am?
NPTEL will give the access for all the recordings.
I
And
mean, this recording, I'm talking about
yeah,
this
these
one.
recordings, yeah, they will give
The
access.
Okay, okay, fine. Because
Okay,
I missed yesterday's also, and today I there was an internet issue. I couldn't join.
okay. Like they will give access to all these recorded sessions.
Okay, okay, okay,
Okay,
ma'am. Thank you.
okay. Uh, so uh, So this is question 9, where it is given that you wish to solve a set of linear algebraic equations written in the form of Ax is equal to b using the Gauss-Seidel method. Which of the following should you have in your computer program? So it is given for that check for diagonal dominance, stopping criterion, iteration count. So Gauss-Seidel method, we all know, we use it is an iteration technique, iterative method to find the solution of the problem. Uh, in Gauss-Seidel, obviously, we'll check for the diagonal dominance. We'll check for the diagonal dominance, and also there will be stopping criterion, like we'll give the tolerance value to check for the uh, to show when it needs to be, when the problem needs to be I mean when the system needs solving needs to be stopped, and also we'll get the iteration count. So like when writing a code for the Gauss-Seidel method, the algorithm will first check for the diagonal dominance, and we'll put some tolerance limit in the program to say when the solution needs to be stopped, like and also we'll take into account the iteration count to see how efficient or how when it when the program is going to be solved, when the program is getting solved. So 1, 2 and 3, all the options are right, so it is given that option D is the right answer. And in next problem, we have that which of the following statements is true about the use of finite difference approximation for solving a given partial differential equations. FD approximation of PDE is applied at all grid points. The same FD approximation must be applied at all points in a domain. So it is given that which of the following statements is true regarding the use of finite difference technique approximation for solving a given partial differential equation. So it is every approximation of the partial differential equation is applied at all grid points. It is mostly not applied at all grid points because we know the boundary conditions. So boundary condition values will be known at the entrance and the exit regions, mostly values will be known. Same FD approximation must be applied at all points in a domain. It is also not true because in most problems when the geometry is complicated, the same FD approximation will not be used. I mean, it will not be efficient to use the same FD approximation. So there will be different things can also be used to if it is a complex geometry. So that like 1 is also not true, 2 is also not true, obviously. So the answer is neither 1 nor 2 is right. So these are all the 10 questions. We'll just quickly go through all the problems. Or before that, if anyone has any doubts regarding any questions, we'll solve it and we'll quickly go through all the problems once again.
Madam, can you explain question number
Question number
10, madam? Last question.
yeah, like it is given that which of the following statement is true regarding about the use of finite difference equations. So in CFD, normally what you do is you will have a certain geometry and you will discretize that geometry. For discretizing the geometry, you will be using finite difference technique. Finite difference technique is nothing but here we have seen, right, how to how to discretize this segment into different points. Like we'll be, if this is a geometry, we'll like this geometry we'll be discretizing it into grid points, and we'll be like, we'll most probably if, consider this rectangular or square geometry. So we'll be discretizing it into equations like this. So obviously, because of the boundary conditions, the values are this and this will be known. So we'll like, we need not use finite difference at these wall conditions. The values will be known from the geometrical identification. And also, like, so FD approximation of the PD is not applied at all grid points. That equation is not applied at all grid points. And in the next case, it is given that same FD approximation must be applied at all points in a domain. Like, what I'm saying is, this is one of the approximation. Like, in, if it is not efficient in giving the solution, the approximation, like it won't be the same delta y in all the cases. Like, in most cases it will be equally divided, but in some cases, if it is not efficient, there will be discretizing will be different. So it is the same FT approximation need not be applied at all points inside in the domain. So both of these statements are not true in the context.
Okay, madam. Okay. Thank you.
Ma'am, I have one doubt.
Yeah.
As I use, ma'am, जो first question है,
Okay. Yeah.
can you
This
please?
question.
Yeah. So,
Okay.
in this question, like curl square u upon curl y square. So इसमें हम जो j minus वन and minus टू यूज, ये मैम इसका डेरिवेटिव करके ले रहे हैं और समथिंग एल्स?
Uh, I mean, can you repeat the question? Like,
I'm I'm asking like curl square u upon curl y square at grid
yeah.
points. Yeah, yeah, yeah. So if we put it equal to something like its derivative, so how we see the this, right?
This
So
one.
yes, yeah. So how we obtain the other
This one.
RHS? Yeah,
Okay.
yeah.
So it is like, you will be using this is a second order derivative, right? Uh,
Okay.
like for first order derivative, you have a certain equation, and you like, say, central difference scheme, you will be using it, right? I mean, you know the central difference scheme for forward difference, backward difference, right? Or no? I mean, anything is fine.
Yeah.
I mean, I'm asking, like,
Yeah,
you
ma'am.
you you know central difference scheme or not?
No, ma'am. I'm not.
Okay, okay. One second, then I'll just show you. Can you just wait a minute? I'll just show you.
Yeah, ma'am.
So it is like in central difference scheme. Mm, it is we'll consider 2 points like we'll consider 3 points like this. In this is in y direction, right? So the I factor remains constant. We'll keep it as I comma I and j, and this will be then u I j minus 1 I comma j plus 1. So in central difference, what you will be getting to see is that uh, it will be u I comma j plus 1. To get the value at this point when you are using for central difference, this one can you just see this? Is this clear, or do you want me to write by some other means?
No, ma'am, it is clear.
Okay. For uij plus 1 minus u I j minus 1 divided by 2 delta y. This is for first derivative. Where it is like dou u by dou y at I comma for dou dou y at I comma j by central difference scheme. If we want to know the first order derivative at this point, we use like ij plus 1 uij plus 1 minus uij minus 1 by 2 delta y. This is for first order derivative. If it is of a forward difference, just for information, not in this just for information, we'll be using these 2 points, that is uij plus 1 minus uij by delta y. That will give forward difference, and backward difference, if we are using, it will be like uij minus uij minus 1 by delta y. If we use these 2 points, it is backward difference, and if you use these two, it is forward difference.
Okay.
Like when you are using this point and this point, like to get the central points, this is known as central difference formula. In central difference, for getting dou u by dou y at I comma j, you will be using uij plus 1 minus uij minus 1. To get the point value at I comma j, you will be using two different points at I j plus 1 and j minus 1 by 2 delta y. So here it is given that for second order derivative, similar way we should find. Similar way in the sense, dou u, like dou square u by dou y square at I comma j, it is like dou by dou y of dou u by dou y. So to at I comma j. So according to central difference formula, we will be having that this will be equal to dou u by dou y at I plus I j plus 1 minus dou u by dou y at I j minus 1. So divided by 2 times delta y. Like we know the dou u by dou I j plus 1. If we substitute u I j plus 1 minus u I j by like similar to this, we'll get one central difference formula, right?
Yes, ma'am.
Like what I'm saying is you understood this part, right? How we are getting central difference for first order derivative. Like if
Yes.
we are getting at I comma j, it will dou u by dou y at I comma j will be u I j plus 1 minus u I j minus 1 by 2 delta y.
Yeah.
Similarly, for getting a central difference for the dou u by dou square u by dou y square, to get we'll be using a differential derivative of a derivative, that is dou by dou y of dou u by dou y at I comma j. So similarly, how we have done here, we use like dou u by dou y at I j plus 1 minus dou u by dou y at I j minus 1 divided by 2 delta y.
Okay.
So if we substitute the central difference value for dou u by dou y at ij plus 1 and the central difference value of dou u by dou y at ij minus 1, we'll be getting a formula similar to this 2 delta y. And bottom again 2 delta y will be there. Like it will come in uij minus 1 to uij. So you'll be getting this form.
Okay, ma'am.
If you just try it out once.
No. Yes, ma'am. Okay.
Okay. But I guess here 1, 2 would be coming. Any like any other doubt?
No, I'm not right now.
Okay, fine. Is there any doubts for someone else?
Mm,
Yeah.
ma'am, I have a few questions apart from the like this course.
Okay.
Just regarding CFD.
Like
Ma'am, like I'm a third year student from
okay.
in mechanical branch. So I'm just started about learning CFD. So I've heard about NPTEL is providing me this course, so I've just enrolled for that.
Okay.
But I think there is a lectures only for like pen and papers point of view. But I want to learn also about like on software basis like open form with the help of MATLAB coding and
Okay.
so how can I go for that?
Like for specific softwares, there would be tutorials. I don't know about other NPTEL courses. You can try it online. If it is available, you can join. Or else there will be so many tutorials available on the internet for usage of those softwares.
No, and basically, I want to know about that as we go for CFD. Basically, CFD is not just an individual subject; it is combination of mathematics, also and fluid that we studied in our fourth or fifth semester in BTech. So I want to know how we should command over all that.
It is like if you understand what concepts it is being taught in this course, like very thoroughly, you will be able to, I mean, try coding on that on your own.
Yeah.
Like step by step you start and you'll be able to do something, and side by side if you want to learn specific softwares like OpenFOAM, you can try it. Like in there will be tutorials separately available on the internet, you can try on those.
Okay, ma'am.
Okay.
Madam, can you slowly show each question, madam, to note down?
Yeah, like we'll first solve the doubts and then we'll go again.
Okay, ma'am. Okay, ma'am.
Okay. Like 5 more minutes we'll solve the doubt session, and we'll go through all the questions once again. Like if anyone is having any doubts in this session, like you can ask. Okay, if there is no question, we'll just go through these questions once again. So the first question is basically asking which of the following formula is a good approximation for dou square u by dou v square at grid point I comma j. And for getting these, we saw like discretization, and one more approach would be, we'll just say, yeah. So like we'll just see, like we all know Taylor's approximation, right? So for the point to get Taylor's approximation at I comma j plus 1, we'll consider I comma j plus 1 point. So this will be equal to u I comma j I comma j. Since it is I comma j plus 1, we'll go in the forward direction, that is u I comma j plus dou u by dou y, uh, like dou u by dou y at I comma j into delta x, I mean sorry, delta y, for since we are going in the y direction, delta y plus same thing will come like delta y square and so on, like when we are considering up to second order derivative, this is the approximation for finding u I j plus 1, where we use the u I j I comma j and dou u by dou y at I comma j into delta y plus dou square u by dou y square at I comma j into delta y square. This is Taylor series approximation for finding the point u I comma j plus 1. Similarly, for finding the value at I comma j minus 1, we use I comma j, the formula remains the same, and this will be like minus, and all other things remains the same. So in from if we add these two equations, that is equation 1 and equation 2, what we'll be getting is 2 times this one is equal to uh, u I comma j plus 1. So when we add these two equations, we'll get this form with the approximation error will be there, but we are neglecting it for time being. And to get the dou square u by dou y square into dou square u by dou y square alone, we'll be getting this, which will be equal to all these u I plus j plus u minus 1. This term will go that side. And everything divided by 2 times delta y square. This is how we are getting this equation. It should be 2. Sorry. So this is how we use central difference scheme to get the equation to get the derivative, second or for second order derivative at various grid points. This is one of the method, or like previously said, we can use dou square u by dou y square is equal to dou by dou y of dou u by dou y at point I comma j, and use central difference scheme for first order derivative separately and then differentiate it again to get the second order derivative. Both ways it will give the same result. So this is question 1, and question 2 was asking for a steady developing laminar flow and a circular pipe, and asking for which of the following statements were true. For that only we saw this profile where it was showing that in a cylindrical column, F fluid is flowing and it is a steady state flow and laminar flow, and it is a developing flow. So it is, since it is not fully developed flow, the velocity profile, it is varying axially as well as radially. So option 1 and option 2, both the options are right. And when considering the pressure change in this flow in the circular pipe, it can be seen that the pressure initially it decreases abruptly to a certain extent, and then it becomes linear change in the fully developed flow. So the pressure varies linearly in the axial direction is not true when considering the whole regime, and also the pressure remains constant. This statement is also false because the pressure here is not constant. So only option 1 and option 2 are right. Option 1 A and B are right. Sorry, option 1 and 2 are right. So obviously option A is the correct answer. So next is asking for consider a one-dimensional flow governed by d square u by dy square is equal to c over a height h where the interval h is divided into 30 equal segments. Now here it is given that upper wall moves to the right at a speed of 1 meter per second while the lower wall is stationary. So how many discretized equations will be there? It is asked in this question. So 30 equal segments. So basically, consider a very small system. Here it is given that it is equally divided into 3 segments. For 3 segments, we got 4 points. So when considering that, and if it is a small system, we know that value at this point, since it is given that in a flow, this wall is moving at some speed and this wall is stationary. So obviously we know the value at this point and as well as this point. So how many discretized points that are remaining is 1 and 2. 2 points are remaining when 3 segments are considered. Obviously when 30 segments are considered, it will be 30 minus 1, that is 29. When considering all the points, it will be 31 discretized points where we know the values at the boundary conditions, that is top and the bottom. So it will give 29 discretized equations to be solved. Next is the
Hello, ma'am.
yeah.
Why are there 31 discretized points and not 30? Because we start the gridding from the first division, right? So that is always beyond the boundary, not at the boundary.
No, we'll be considering everything, right? What I'm saying is you will not be discretizing, in the sense you will be considering all the points.
Okay, okay.
Like this point will also be considered for calculation. In that way, I am mentioning as discretize, like I am mentioning it, I am considering it to be one of the points. But how many equations remaining will be 2.
Yes.
So in that sense, if it is a large system, it will be 29 equations for 30 segments.
Yes, ma'am. Got it.
Okay. Yeah. Okay. So the correct equation governing flow in a fully developed flow through a rectangular duct is, some options are given. We will see which of this it fits. So for a fully developed flow through a rectangular duct, consider the flow in the x direction. So obviously u velocity alone remains, v and w becomes 0. On also the u is the function, u will be varying along y and z. No, it won't be varying along x. So this is the Navier-Stokes equations for flow through the rectangular duct in the rectangular coordinates. So we'll see how this equation can be simplified. So considering a steady state, it does not vary with time, so this term becomes 0. And also the v velocity and w velocity becomes 0. And also u does not vary along the x direction, so this term becomes 0. On the whole, this whole term in the left hand side becomes 0. And we are not considering the gravitational effect, so this term becomes 0. So minus dou p by dou x remains, this term remains, and here it is again this dou u does not vary in the x direction, so it becomes 0. Remaining all the term is present. So when this term goes in the other side, we'll get, and mu is transferred to this other side, we'll get dou square u by dou y square plus dou square u by dou z square is equal to 1 by mu dou p by dou x. So which is option B. So next is D. Consider a fully developed laminar flow through a square duct of side L, and that through a rectangular duct width to height ratio of 2, such that both of them have the same cross-sectional area. Same fluid flows through both the ducts at the same volumetric flow. Which of the following statement is true about the two flows? So it is from this statement it is observed that governing partial differential equation, it remains the same. So governing partial differential equation is the same in both the cases. Wall boundary conditions are the same, though these are applied at different locations. This is also true since the dimensions of the square duct and the rectangular duct are different. Their application is different at different locations. And option 3, it is given flow domain is the same, which is false, because flow domain is not the same in both the cases, because here the width to height ratio of rectangular column is different than the square column. So obviously flow domain is not the same. So option 1 and 2 are right. So it is answer C. C is the correct answer. So next for following 3 questions, we have one case where it is given that you wish to solve a problem involving steady heat conduction in a slab of thickness L. If the wall has a volumetric heat generation rate Q, if the height and breadth of the slab are very large compared to L, then one can assume the problem to be one-dimensional. Here it is for the case of constant thermal conductivity, the equation governing temperature distribution takes the form K is equal to d square T by dy square is equal to Q, where K is the thermal conductivity of the material, T is the temperature, Y is the distance in the thickness direction from one end of the wall, and Q is the volumetric heat generation rate. For this case, the calculation domain encompasses the region y is equal to 0, L with both boundaries included in the calculation domain. What are all the points that can be observed from this is wall has a volumetric heat generation rate, it is Q, and heat height and breadth of the slab are very large compared to L. So the problem is assumed to be one dimensional. So for this case, the thermal conductivity is assumed to be constant. So the equation in this case is given as this. So the main things to be noted is it is one dimensional problem and the thermal conductivity is given constant in this equation. So the equation is this for this case. So from this case, we will see few questions in analyzing the equations. For equation 1 to be dimensionally consistent, the units of Q should be so Q is equal to K d square T by dy square. We have given this. So K is the thermal conductivity given by watt per meter Kelvin and K temperature in Kelvin. Y is the distance in meter. And Q is the volumetric heat generation, the unit of which we need to be finding. So we will be substituting the values for this in this equation, where Q's equation is watt per meter Kelvin into Kelvin per meter square. If we substitute for watt, the equation in the SI unit, we'll get this kg meter square per second cube per meter Kelvin into Kelvin by meter square. On simplifying this, we'll get it is kg per meter second cube. So which is option B. To get dimensionally consistent, we need to substitute all the known units for other terms in the equation. So we'll get the equation for the unknown, so such that it will be dimensionally consistent. All units should be logically be equal. LHS and RHS should be equal for the dimensionally consistent case. So, which of the following cases is not permitted by the equation 1? K d square T by dy square is equal to Q. This is equation 1. Thermal conductivity is dependent on temperature. Thermal conductivity is dependent on location inside the calculation domain. That is, this is T and this is Y. So, these two statements are mentioning that K, that is thermal conductivity, is a function of T or Y. But we know that K is a constant in this equation. So thermal conductivity is not dependent on temperature. Thermal conductivity is not dependent on location inside the calculation domain also. Both the cases are not permitted in this equation. So it is option C is the correct answer. For equation 1 to be used to find the temperature distribution along the length of the rod, which of the following conditions must be met? The rod must have L by D is very much greater than 1. That is, since this is a rod, we are assuming that length is very much greater than diameter of the rod, so that the flow along the length of the temperature distribution along the length of the rod, we can assume it to be one dimensional, and so we can use equation 1. Equation 1 is Q is equal to K d square T by dy square. So to use this equation, it was assumed one dimensional in the given case. So Here also, if we want to use equation 1, it should be one dimensional. So length must be very much greater than diameter of the rod, and rod must have its curved side insulated. It need not be true. And rod must have rectangular cross section. It also need not be true. It can be given for any cases, but it should be one dimensional. So option 1 only, I mean option A, that is 1 only needs to be met to achieve this condition. Answer is option A. Next
Ma'am,
is,
can
yeah,
I ask a question?
yeah.
Why is 2 not necessary? If the curved side is not insulated, then by convection also heat loss will occur now.
But it need not be for this case. Like, we are just assuming majorly the application of Q's, for us to use Q is equal to, I mean, this is from the related to the case given. In this case, the major point to be taken is constant thermal conductivity, and it is a one-dimensional case. So to get the application of this equation, it is sufficient if L is very much greater than D. Like, this is these questions are followed by the given case. So we can match it with the scenario and match it for this problem.
Okay.
And it is, you wish to solve a set of linear algebraic equations written in the form of Ax is equal to B using the Gauss-Seidel method. Which of the following should be in the computer program? When writing the computer program for Gauss-Seidel method, what are all the things we need to be checking? The first is checking for diagonal dominance. Whenever we are using Gauss-Seidel method, obviously we'll check for diagonal dominance. And I also will mention this some criteria like tolerance limit, when the iterations should stop. So the stopping criteria will be mentioning, and the iteration count also will be mentioning in the program, so that we know for how many runs it is going on. So obviously all three things will be mentioned in the computer program. So the answer is 1, 2 and 3. So it is option D. And next is, which of the following statement is true about the use of finite difference approximation for solving a given partial differential equations? Finite differential approximation of the partial differential equation is applied at all grid points. It is not applied at all the grid points. We use it only in the in between grid points, not at the boundary conditions. The same finite different approximation must be applied at all points in the domain. uh, if it is a complex geometry, the same finite difference approximation is not applied and at all the points. It would be different for, like, they most programs, it would be changing to suit the complexity of the geometry. So both of the statements need not be true in all the cases. So neither one nor true, nor two, for is true about the use of finite difference approximations for solving the given partial differential equations. So these are all the questions we solved for today. If anyone is having any questions related to this, you are free to ask. Next week we'll be seeing many problems because there is more time, so we'll see more problems in the coming weeks than 10 questions.
Thank you very much, Ankara. You have given that is the problems very patiently. Thank you very much. I don't have any questions, but I asked before only.
Okay.
So thank you very much.
Yeah, thank you for your feedback.
Thank you, ma'am.
Yeah, thank you.
May I leave the session if
Yeah,
I
yeah.
don't have anything else?
If you don't have any questions, you can leave. That's all for today's session.
Okay,
Like
thank you.
we'll see more problems because we have more time left now. In the future classes, we'll plan accordingly. Yeah, sure. If if you people are not having questions, you can leave.
Thank you, ma'am.
Yeah, thank you. Excuse me. Before closing the session, we'll just go through all the problems one by one for clarification before closing it. So first we saw how how to approximate the given partial derivative at the given grid points I comma j. So for that they have given 4 options. Out of 4 we have to get the solution. We use using central difference scheme and partial difference first order and second order derivative, we get the following equations. Answer D, the answer is none of the above. So how it is, we got 2 methods. The method 1 is Taylor series method, and from this we get approximation for 2 and we add that and we obtain the final equation. And the next method is we first approximate it by using central difference scheme and then substitute the forward difference scheme and the backward difference scheme, and we get the final differential equation, final derivative in the form of grid points. And next is a steady developing laminar flow in a circular pipe. Which of the following statements are true? First, they have compared velocity profile and pressure profile. So this is the velocity profile and this is the pressure profile. Velocity profile keeps varying axially as well as the radially, whereas the pressure profile keeps varying. It does not remain constant. It does not vary linearly also. After some points it varies linearly, but before that it is not varying linearly. And next is the H is divided into 30 equal segments. Upper wall moves at the speed of 1 meters per second while lower wall is stationary. Number of discretized points. So based on this we get if it is divided into 3 segments, we have 4 points, and of these 4 points we know the value at top and the bottom, so it is 2. Similarly, for 30 segments, we'll get 31 points and it will be 29 equations. This is the correct equation in the flow through a rectangular duct. We use the Navier-Stokes equation in the rectangular coordinates. And we use substituted like steady flow, and U is not a function of x, and V and W are 0, and we use G is 0 and it is again 0. Other terms put together we will get this form of equation. Fully developed laminar flow for the square duct and the rectangular duct. Square duct and rectangular duct varies in cross section, so flow domain is not the same. Other things like governing partial differential equations same, and the wall boundary conditions are the same. So it is a one-dimensional problem for a given case. We need to study the case and then apply it in the following questions. They ask for the unit of Q. For that we should dimensionally consistent. We should substitute other known equations and get the unit in this form. And next is the which of the following is not permitted by this equation? That is, thermal conductivity is not dependent on thermal. It is a constant value, so it is not dependent on temperature or location. And since it is a one-dimensional problem, the major criteria must be L by D should be greater than 1. For Gauss-Seidel method, we check for diagonal dominance, stopping criteria, iteration count. And for final difference approximation, we get the need not get equation at all points, and the same FD approximation must be applied at all and must apply at all different points is also false. So both of these equations are false. Thank you. We'll see in another session. So thanks for your attending the session. ஹலோ முடிஞ்சதுக்கா நீங்கள் இந்த ஒரு நிமிஷம் வந்துடுறேன். சரிக்கா, பை.